In today's video, we're going to be talking about continuity over the open and closed interval. In the last couple lessons, we've been talking about continuous functions, which are functions that do not have any jumps or disconnects across the domain. And we're going to continue talking about that with open and closed intervals, except our domain gets shrunk even more. Let me explain with some definitions. First of all, the open interval. A function is continuous along the open interval represented by a comma b with parentheses. This will be important when we talk about the closed interval. The open interval is with parentheses. If f is continuous, by the way, continuous is C-O-N-T with a dot. That just stands for continuous, but shortened because it's a long word. If f is continuous at every point along a comma b. Now, I won't lie, this definition is not very intuitive. It tells you it's continuous if it's continuous, but this will make a little more sense when we do examples. But first, let's talk about the closed interval. The closed interval is the same as the open interval. But, of course, there is one main difference. As the open interval, a comma b, but this time, the endpoints are included. And this is also denoted as a comma b with brackets. So why do I use brackets on the closed interval but parentheses on the open interval? Well, the open interval is with parentheses because the endpoints are not included in the domain of this function. With the closed interval, the endpoints are included in the domain of the function. So that's why we denote that with brackets instead of parentheses. But you may notice that I wrote the definition for an open interval in terms of how it's continuous across the open interval. So how does a closed interval become continuous? A closed interval is continuous if the open interval AB, remember this does not include the endpoints, is continuous, and the limit as x approaches a of f of x equals f of a, and the limit as x approaches b of f of x is equal to f of b. So what do these limits down here even mean? Why are they within this problem in the first place? Well, essentially this closed interval definition is saying that as long as the open interval is continuous, the closed interval can also be continuous as long as the function is continuous at the endpoints a and b. That is the only difference between them, and that's what these limits are saying. Essentially, if we plug in a to our f of x, we expect it to equal f of a. If it doesn't, that means there's a jump or a discontinuity, and that's true for f of b as well. But to further explain what I'm talking about, let's do an example over here on the right, and I'll leave these definitions up as a reference. And just for fun, let's use the red pen. So here we have the xy plane, looks something like that, and we're going to draw a function that I know you know. The lovely y equals x squared. But this function is also restrained on a domain. The domain of this function is -1 to 1, and this is a closed interval. Let me just write that up here. A, B, the closed domain, is equal to -1 and 1. So now that we have this information written down, I want you to tell me, is y equals x squared continuous on the closed interval -1 to 1? And let me put brackets around this because I did not do that before. So how will we go about answering this question? Well, we can look at our definition of a continuous function along a closed interval. First, we need to make sure that this function is continuous along the open interval. Remember, the open interval is just the interval, but not including the endpoint. So everything between -1 and 1, but not including those two numbers. So how can we prove that y equals x squared is continuous along the open interval? Well, the main thing is that x squared is a power function. A power function is just something being raised to a power, and our x variable is being raised to the second power, or being squared. Therefore, x squared is a power function. And one type of function that we know is continuous everywhere is a power function, and we learned that in one of my past limit videos, which I'll link here. So since x squared is a power function, and we know that power functions are continuous everywhere, we know for sure that x squared is continuous along the open interval. So check. That's the first thing done. But now we need to check this down here. What we need to check is that our limit of x approaching a of f of x is equal to f of a, and then do the same for b. So what we're going to do is we're going to write down our problem here. We have the limit as x approaches our a value, which is -1 of x squared. What does this equal? Well, all we have to do to solve this limit problem is plug in -1 for our x. So this is equal to -1 squared, which is equal to 1. -1 times 1 is equal to 1. But we're not done yet. This has to equal f of a. In other words, we need to plug in a to our function, which is x squared, and see if that is the same as 1. So let's plug in a, -1, to x squared, which is just -1 squared, which is equal to 1. And as you can see, these two are equal. Therefore, the first part of our closed interval continuity rule is true. The limit as x approaches a of f of x is equal to f of a. If f of a or f of x were different, then there would be a jump or a discontinuity somewhere along this function, but there does not appear to be one here. Now let's do the same thing for our other endpoint, which is b, which is equal to 1. So the limit as x approaches 1 of x squared is equal to what? Well, we can do the same thing as last time, which is just plugging in 1 to our function, which is equal to 1 squared, which is equal to 1. 1 times 1 is just equal to 1. And once again, we have to make sure that this limit that we just did over here is equal to f of b. So now we need to plug in b, 1, into our equation. So if we plug in b to our x squared equation, this is equal to 1 squared, which is equal to 1. And as you can see, these are also equal. Which means that we have now satisfied the closed interval rule as well. Not only is this function continuous in the open interval, but it is also continuous on the closed interval, including at the endpoints, which we just proved by doing these limit problems over here. Which means that this function is continuous along the closed interval. Write a big ol' yes to celebrate, why not? Let's do one more example so that way you get the hang of it. In our second example, we once again just have the xy plane as such. But we have this function. It looks like this. And you may recognize this function as y is equal to 1 divided by x. And this is within a closed interval. From here, which is -3, to here, which is 2. I'll write that down up here. Our closed interval a comma b is equal to -3 comma 2. So I want you to answer this question. Is our function continuous along this closed interval from -3 to 2? Let's answer that. First, we need to see if this function is continuous along the open interval. Remember, the open interval is just the closed interval, but without the endpoints. But you may notice one problem. There is a big vertical asymptote right here, right down the middle of our closed interval. And there's a reason for that. If we were to plug in 0 for our function, we would get 1 divided by 0, which of course does not exist. We can't do that. That doesn't work. It doesn't make any sense. Dividing by 0 is illegal in math, and also in 12 states. So since we know that this function is not continuous just along the open interval, we don't even have to test these two down here because we already know that it's not continuous across the entire closed interval. So this function is not continuous along this closed interval. Now, if our closed interval was something like, let's just say we had a closed interval from -5 to -3 like this, then this function would be continuous along the closed interval. We don't have this vertical asymptote in the middle preventing this function from being continuous. But since we do go across the vertical asymptote, this function cannot be continuous along that closed interval. I hope this video helped you out today. Consider subscribing if you need more calculus help because I am your guy for that. Oh, and watch this playlist because that playlist has every single Calc 1 lesson on this channel. I'll see you guys in the next video.